Hello pre-calculus students, and welcome to a video that's a continuation of our lesson 4-2, which is from section 2.5 in your textbook, on horizontal reflections and dilations, which is going to complete the picture of transformation rules. Alright, so let me first this is where we left off. We just finished graphing this function, and I just wanted to point out one more thing about this. So once we have it graphed and we notice that we have our stretches here, this reflected and then stretched, I want you to also notice that if you take the points, like for example 1, 1, let's put it down here, and you multiply so that if the y's were the same, the x's were doubled. So if the y's stayed the same from xy, then what would happen is you double the x's. That's what we found when we say stretched by 2. And then reflected, we actually have to multiply it by a -2. So actually what we're doing is we're multiplying it by 1 over a, which is 1 over -1/2. That gives us a -2. And that's with the y unchanging. So what we're really looking at here is the point 1, 1 is going to go to -2, 1. That's what you have right there. Okay, and the point 4, 2 goes to -2 times 4, which is -8, and then the y doesn't change, so that's the 2. This is a really nice, fast way to do these, and I'm going to show you these in one more example after I do the last example just the same way. Okay, so this is using transformation rules, and the trick is just to get this rule. Once you get the rule right and you have a couple points, usually there's 3 points on the parent function, you got the graph, and it's just one step. No need for a parent function, no need for anything else. Okay, let's look at the last example. So the last one here, y equals 1 over 2x. Okay, so the first thing is to recognize that the function is y equals 1 over x. Okay, and then the second thing is to recognize that here, actually this should be around the whole thing, that a is on the inside there, the a is 2, so a equals 2. And so that means what's going to happen is this, since a is 2, we want 1 over a, we're going to get a horizontal compression, because 2 is more than 1, compression by a factor of 1 over 2, or 1/2. So if we graph our parent function, it's going to be compressed by a factor of 1/2. For this one, I think we need to make the scale a little bit different. So that's going to be our 1, 2, 3, and that's going to be our 1, 2, 3 horizontally and vertically. So there's 3, there's 3. And let me just put it in all directions. And I'm going to plot the parent function, which sometimes is the one that you guys are maybe the least familiar with. So this is going to have the point, the parent function has the point 1, 1. It has the point, now this is the parent right here, so it has the point, if we plugged in 1/2, we would get 1 over 1/2, which is 2. So it has 1/2, which if this is 1, this is 1/2, and then up to 2, so it has a point right there. If we plug in a 2, the output is 1/2, so they're kind of like, they're just reversing that same process. So over 2, up 1/2. So this is one branch of the parent function, and then the other branch, this is an odd function, so the other branch is just over here. So it's got the same idea here. Instead of going over positive 1/2, we go over -1/2 and down 2. Instead of going over positive 2, we go over -2 and down 1/2. So this would be the full graph of the parent reciprocal function. All right, now let's look at the transformed reciprocal function, where we're going to horizontally compress it by a factor of 1/2. That means that where there was a 1 here, at the same height, there's going to be a 1/2. Where there was a 2 here, at the same height of 1/2, there's going to be a 1. And when there was a height of 2 here, and the x was 1/2, it's going to actually go all the way down to 1/4. And so this is what it's going to look like. A little bit hard to squeeze that in there, even though I changed the axes a little bit, but there it is. And the same thing happens over here. At the same height, it's going to be compressed by a factor of 1/2. At this height here of -1/2, it's going to be compressed from 2 to 1. And at this height here of -2, it's going to be compressed from -1/2 to -1/4. And there's the graph. Now, it's asymptotic, so we're not supposed to really touch the axis there, but that's that. Now, I just wanted to kind of point out, and I think you might have seen this in the notes depending on which class you're in. Another way to look at this, instead of thinking of that 2 in the denominator and part of what is the x, so that would be making it the inner function, and that's why I try to put these parentheses here, so it's the inner function. You can also think of this as 1/2 times 1 over x. Hopefully you agree that that's also equal to 1 over 2x. So, but this is looking at the 1/2 on the outside, which means it's not inversely related, but it's actually a compression vertically by a factor of 1/2. Right? So this is a vertical compression because it's on the outside, it's vertical. So this is a vertical compression. And you can see that here too, because here's a point that has a fixed x value of 1/2, but the y gets compressed down to 1/2 its height. And that happens everywhere. This y gets compressed down to 1/2 what it was. This y, which is a value of 1/2 here, gets compressed down to 1/4. That's half of 1/2. And the same thing with the negatives. Okay. So that's that example. Now, I posted something on this assignment page that I want to show you. And it's just a little reference that pretty much shows all of the rules and what happens. Now we're going to look at the big picture just for a moment here. So this is also part of 4.2a. And this just shows you all 3 transformations. These are the same 3 transformations as you learned in geometry. And you can see that when you're talking about a translation, what happens is if the k is on the outside, a lot of times we call it k, and then the h is on the inside, you can see what happens is if the k is on the outside, if k is greater than 0, it goes up. If k is less than 0, it goes down. While on the inside, if h is greater than 0, it goes to the right, so it's kind of backwards, right? If you subtract a positive number, it goes to the right, while if you subtract a negative number, it goes to the left. Like if you add a number, it goes to the left. So that's what we saw. So there's the inverse in this summary. The reflections, all you got to do is remember if the negative's on the outside, you're looking at anything on the outside is vertical. A vertical reflection means it would go up and down, which is over the horizontal line, right? It's got to go over a horizontal line because it's reflecting vertically. All right, and then down here, the dilations, and this is one of them that we added on right here. But if it's on the outside, then it's a direct relationship. So we can see that in here. So anyway, this is pretty useful. All right, now here's a really nice summary putting it all together. I just changed the letters, but I'm going to tell you what each one of them means. So this is our general function now. This can be any of the parent functions that you know, and anything that you learn in the future, you can apply the same rule for transformations, putting them all together. And so in this rule, they're all here, all of what happens with each one of them. Notice that the 2 that are on the outside, which is the A and the D on the outside, they affect the graph vertically. And when they affect the graph vertically, they have a direct effect on the graph rather than inverse. And the stuff that's on the inside of the function, this would be, if it's an absolute value, it'd be something that's inside the absolute value. That's maybe the easiest one to see. If it's a square root, this would be the stuff that's inside the radical. If it's a square function, this would be the stuff that's being squared, not multiplied by something being squared or something added to it, but something on the inside, etc. Okay? And you can see that these are all horizontally affecting the graph, and they are also inversely related. So I put that whenever it's horizontal and on the inside, it's inversely related. And this is an order that you can do it in that will not cause you any problems. And it's basically, and I chose this order to explain this because it's basically working from the inside out, following order of operation. If you were to follow order of operation, just looking at this, you would do the inner stuff first, which is first. Then you would do the stuff inside of these parentheses, which is second. Then if you have a choice between multiplication and addition, you would always multiply first, right? So we do that next, and then the addition would be the last thing. And if you do that, you won't run into any trouble. The thing is, you got to have the function in that form. So let's look at one example and see if we can do this in 5 minutes, okay? Okay, So here's an example of an absolute value function that has everything going on with it, every single possible transformation. And what I'm going to do is I'm going to show you how to do this using a transformation rule, using the idea of the inner function and the outer function. And what we're going to do is we're going to make a rule that tells us what x, y goes to, exactly what happens to each point, looking at a couple of basic points for y equals absolute value of x. The parent points, which would be 0, 0, 1, 1, and negative 1, 1. If you graph those points and you know the basic shape, you're going to get, your basic absolute value function that looks like that. Okay, but that's not what this is. This is a transformation of that, pretty much every possible transformation. So what we want is we want to know this rule. We want to know what happens to each x here, what happens to each y, what our 3 points will be, and then we've got the graph. All right, so the outer function is the y's. The outer function is the stuff on the outside of the absolute value. So it's pretty simple because it's direct. So we can just pretty much write it down. It's just negative 3y minus 4. That's all, because this is the y, this is the inner function. So this is negative 3y minus 4. Pretty simple, right? The inner function, not quite as simple because it's not directly related. But remember, from here, the inner function is always going to be inversely related. So we're going to go back and we're actually going to create an inverse. So we're going to look at this inner function as its own separate function. Once you get used to this, this is by far the fastest way to graph something like this, in my opinion. All right, so this inner function, I'm just going to write this as a function. So f of x equals 1/4 x plus 1/2. And I just want the inverse of that function. So this is like y equals 1/4 x plus 1/2. To find the inverse, you switch x and y, so this would be x equals 1/4 y plus 1/2. And then you solve for y. That's how you find the inverse. So we're sort of unwrapping it. We're going backwards. Subtract 1/2 from both sides. X minus 1/2 equals 1/4 y. Multiply both sides by 4. 4x minus 4 times 1/2 is 2 equals y. That's the inverse. So this means that f inverse of x, the inverse of that inner function, is 4x minus 2. All right. So now we're going to look at that and put that in here. That's our inner function. It's that simple. Once you find it, you've got your rule. Now once you have your rule, you just apply your rule by plugging the x's in here and the y's in here to get your 3 ordered pairs. So when I plug 0 in here, I get negative 2, right? When I plug this 0 in here, I get negative 4. That's the new vertex. When I plug 1 in here, I get 4 minus 2, which is 2. When I plug 1 in here, I get negative 3 minus 4, which is negative 7. When I plug in a negative 1 here, I get negative 4 minus 2. I'm just focusing on the negative 1. Negative 4 minus 2, which is negative 6. And when I plug in a positive 1 here, I get negative 3 minus 4, which is also negative 7. That's it. Plot those points. You have the transformation of this function. So, quick plot here. I'm not even going to use a ruler because we only have less than a minute left. I can keep these under 15 minutes. And so we have negative 2, negative 4. We have 2, negative 7. So 2, negative 3, 4, 5, 6, 7. We have negative 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6, 7. And hopefully it will look, like it's an absolute value, and it is. And there you go. That's the new graph. So again, this was negative 2, negative 4. This was negative 6, negative 7. And this was 2, negative 7. The other beautiful thing about this is that if I ask you to tell me the points, you've already done the work. The only real work here is when there's a lot of stuff inside and you have to do that inverse. You have to find that inverse.